Problem number 22. A cannon just above the surface of a spherical planet with mass m and radius r launches a particle with the speed v, where v greater than square root from gm over r and less than square root from 2gm over r. The initial velocity of the particle makes an angle theta with the vertical direction. Neglect drag. For what theta will the particle never collide with the planet? Solution for problem number 22. The launch speed is above the circular orbit speed and less than escape velocity. So in any case, orbit will be elliptical, and if angle is exactly 90 degrees, the launch point is the closest point of the elliptical orbit. So it means that in that case, the particle will never collide with the planet. But in other case, orbit of this particle will cross the surface of this planet. So that's not good. It means that only for angle 90 degrees we have good result. So it means that D is correct answer, and that was a solution for problem number 22. Problem number 23. A mass attached to a spring is performing simple harmonic motion with velocity v as a function of t and acceleration a as a function of t. Which of the following could be a graph of the curve a as a function of v over a complete oscillation? Solution for problem number 23. If displacement has a dependency from time as amplitude a multiplied by sine omega t, in that case velocity and acceleration have a dependency like this. And this is exactly parametric equation for ellipses. It means that the correct answer is C, and that was the solution for problem number 23. Problem number 24. A ramp with a height h is moving with a fixed uniform speed v to the right. A small block of mass m is placed at the top of the ramp and is released at rest with respect to the ramp. The block slides smoothly to the bottom of the ramp and onto the floor. How much kinetic energy does it gain in this process? Neglect friction. Solution for problem number 24. If a block reaches the bottom of this ramp, it has a relative speed to the ramp square root from 2gh. It means that the absolute speed will be v final equal v plus square root from 2gh. And now we can count what is kinetic energy difference for this block. That will be delta k equal 1/2 mv final square minus 1/2 mv initial square, which is after calculations it's mgh plus mv multiplied by square root from 2gh. This is answer C, and that was a correct solution for problem number 24. Problem number 24. A ramp with a height h is moving with a fixed uniform speed v to the right. A small block of mass m is placed at the top of the ramp and is released at rest with respect to the ramp. The block slides smoothly to the bottom of the ramp and onto the floor. How much kinetic energy does it gain in this process? Neglect friction. Solution for problem number 24. First, we can find what is the final velocity of this block after it reaches the floor. That will be square root from 2gh compared to ramp, and V final equal V plus square root from 2gh compared to the flow. It means that the change of kinetic energy will be final kinetic energy, which is 1/2 mv final square, minus initial kinetic energy, which is 1/2 mv square. After calculations, we will get mgh plus mv multiplied by square root from 2gh, which is answer C, and that was solution for problem number 24. Problem number 25. Two masses are initially at rest, separated by a distance r, and they attract each other gravitationally. If their masses are m and 2m, then they will collide after time t. How long would they take to collide if they both had masses 2m? Solution for problem number 25. Here we can use energy conservation and momentum conservation. First, let's use momentum conservation. We have mv1 equal to mv2. It means that v1 equal to v2 and the relative speed v1 prime equal v1 plus v2 or 3 times v2. From energy conservation we have this expression. Now we can use expressions for v1 and v1 prime and find that 1/3 v1 prime square equal change of energy. Here we have r prime, that's current distance between masses, and finally we have v1 prime equal this square root. Now let's see what happens if both masses have mass 2m. In that case, momentum conservation gives us v1 equal v2, relative speed equal 2v2, and energy conservation, this expression. Again, we can use expressions for v1 and v2 using v2 prime and find that v2 prime equal this expression. Now we can find a relation between v1 prime and v2 prime relative velocities for two cases with the same distance r prime. So we have v1 prime over v2 prime equal square root from 3/4 for the same distance. It means that time to take to collide back proportional to velocities. So it means that in second case we have time equal square root from 3/4 t, which is answer D, and that was solution for problem number 25.